Welcome back, everyone. In this extra video, I'm going to walk you through some more practice problems involving intermolecular forces. This should give you some extra practice and help you to evaluate your performance in this area. So for this question, we're going to ask you to do two things. Determine which molecule has the highest boiling point, as well as which molecule has the lowest boiling point. Pause the video and try this on your own, and then I'll walk you through it. Welcome back. So in order to evaluate the boiling points, we need to evaluate the intermolecular forces that are present. The first step in determining strength of intermolecular forces is first to evaluate which types of intermolecular forces are present. For molecules C and D, we can see that these consist of purely hydrocarbons. Therefore, there's no polar bonds, and the molecules are nonpolar. So they'll interact only through London dispersion forces. For A and B, it's a little bit more difficult to tell. Is the carbon-sulfur bond polar? Is it nonpolar? It turns out that we don't actually need to determine whether or not those bonds are polar because of the larger mass of the sulfur atom as compared to the carbon atom. So if we evaluate the shapes and structures and sizes of these molecules, we can rank them in terms of being heavy or light. Note that A and B are structural isomers and C and D are structural isomers. Now, since we've put them into their groups by their molar mass, how do we distinguish between them? Well, in this case, we can do it based upon their shape. And we have two that are extended shapes and two that are more compact shapes. And so the ones with the highest boiling point are going to be the heaviest, most extended. The one with the lowest boiling point is going to be the lightest and the most compact. And indeed, if you were to look up the boiling points of these molecules, they would match our predictions. Note that it would be hard for you to determine is molecule B or C, which of those two has a higher boiling point. So we wouldn't have asked you to rank them absolutely unless each molecule shared one thing in common with each of the others, and you could evaluate. All right, let's try another problem. Which intermolecular force could form between C2H2 and PCl3? Pause the video and try this on your own. Welcome back. So how do we know which intermolecular forces are present? You have to know, is a molecule polar? Is it nonpolar? Do we have hydrogen bonding? Do we have ions involved? So C2H2 looks like this. PCl3 looks like this. So let's evaluate. Neither of these are ions, so we don't have any types of ion interactions involved. C2H2 doesn't have polar bonds, and therefore it's nonpolar. PCl3 does have polar bonds, and because this is a tetrahedral shape with the lone pair electron, therefore it's a trigonal pyramidal molecular geometry that's going to give us a polar molecule. And all molecules interact through or can have induced dipoles, and therefore both of these will interact that way. So how do we know which actual interactions form? Well, you pair up all of the possibilities. We can have an induced dipole with a dipole, so we call that dipole-induced dipole, and then we can have induced dipoles interacting with induced dipoles, also known as dispersion forces. So those are the interactions that could form between C2H2 and PCl3. Let's try another problem. Rank these molecules in order of increasing boiling point. Pause the video and try this one on your own. Welcome back. So in this case, the structures are given to you. So what you need to do is identify whether or not they're polar, nonpolar, could exhibit hydrogen bonding. Molecule number 1 is purely hydrocarbon, and therefore it's nonpolar. Molecule number 2 and molecule number 3 are polar. We also see that molecule 2 and 3 have an increase in molar mass relative to molecule number 1, but they're isomers of each other. So 2 and 3 are both polar. They have the same molar mass. So how do we differentiate between them? Well, you should be able to recognize that because of the hydrogen-oxygen bond here, molecule number 3 can exhibit hydrogen bonding. This hydrogen is covalently bound to a carbon atom right here. Therefore, it cannot participate in hydrogen bonding. So, molecule number 1 has the lowest boiling point because it's the smallest overall and it's nonpolar. Molecule number 3 is the highest because it has a higher molar mass, it is polar, and it interacts through hydrogen bonding. And then molecule number 2 is in the middle. Okay, here's another set. For each of these molecules, indicate which molecule has the higher boiling point and try to identify what's the reason behind it. Welcome back. In the case of diethyl sulfide and diethyl ether, diethyl sulfide has the higher boiling point. What's the rationale here? It's an increase of London dispersion forces due to the higher mass. These have a vastly different mass, and the polarity difference is not very large. So we see that diethyl sulfide has a higher boiling point. How about T-butylthiol versus N-butylthiol? N-butylthiol has a higher boiling point. While these are constitutional isomers, we see that the T-butylthiol is more compact. Therefore, it has fewer London dispersion forces. Diethyl ether versus N-butanol. N-butanol has a much higher boiling point. While these are constitutional isomers, therefore they have the same molar mass, London dispersion forces will be the same. But N-butanol can interact through hydrogen bonding because it has a hydrogen with a covalent bond to oxygen, and there's a set of lone pair electrons on those oxygens. All right. Which pair of molecules could form hydrogen bonds with each other? So, molecule on the left interacting with the molecule on the right. Pause this video and try this on your own. Welcome back. So what we need to do here is identify which molecules could be donors and which could be acceptors. If you have a donor paired with an acceptor, then they can form hydrogen bonds with each other. A donor is when we have a molecule with a hydrogen covalently bound to oxygen, nitrogen, or fluorine. And the acceptor is a partially negative oxygen, nitrogen, or fluorine with a lone pair. Let's evaluate pair number 1. We have a donor and an acceptor. The donor is the hydrogen of the alcohol. The acceptor would be the lone pairs on the oxygen atom. However, the molecule on the right is neither. While we have nitrogens, and while they have a lone pair of electrons, they're not partially negative. This bond is nonpolar, and therefore it's not going to interact through a dipole-dipole interaction. And hydrogen bonding is just a specific version of a dipole-dipole interaction. Okay, pair number 2. This is an acceptor. The oxygen in this molecule has lone pairs of electrons on it and can accept a hydrogen bond. However, on the right, while we do have an acceptor, we have no donor. This hydrogen here is covalently bound to carbon and not oxygen. For pair number 3, we have an acceptor due to the lone pairs of electrons on the hydrogen, and we have a donor because we have a hydrogen with a covalent bond to nitrogen. Okay, this is our last problem of the video. Which one of these substances will not have hydrogen bonding as one of its intermolecular forces? pause the video and try this on your own. Welcome back. So in order to have hydrogen bonding, we need to have both an acceptor and a donor. Oxalic acid can interact through hydrogen bonding with other oxalic acid molecules because it has a hydrogen bond donor and hydrogen bond acceptors. Hydrogen peroxide can interact similarly. Methylamine can also interact through hydrogen bonding, as can methanol. Acetone, while it does have hydrogen bond acceptor with the oxygen atom, there is no donor on the acetone molecule. So it could not interact with itself through hydrogen bonding. It could, however, interact with any one of the other four molecules through interacting through hydrogen bonds. So again, it has an acceptor, but no donor. That's it for this video. Thank you for watching. Have a wonderful day.